Good morning, dear students. Welcome back to physics class. In today's class, I am going to discuss mainly on three topics. They are A. Liquid surfaces, B. Surface energy, and C. Surface tension. First, I would like to talk over some important properties of free surfaces of liquid substances. You know that both liquid and gaseous substances are having a common characteristic. What is the common characteristic of liquid and gaseous substances? Both of them do not have specified shape. They will take shape of containers in which they are occupied. So, you should understand that whenever liquids are poured in any container, they take the shape of that container in which they are poured, whereby they acquire a free surface. What is the nature of free surface of liquid? Consider a case if you pour water inside a glass, you know that it takes shape of the glass. It will have a free surface at the top when it occupies in the glass. Top surface of the glass is a free surface because on top surface water is not in contact with anything else. It is only in contact with air. When water is in the container, it will have interface between the two fluids, water and air. So, it will have a free surface. You also know that the liquid substances are having one distinguishable property from the gaseous substances. They have fixed volume, but gaseous substances do not have definite volume. Free surfaces of the liquids have additional energy as compared to their inner surface. Next topic is surface energy. Surface energy is excess energy exhibited by liquid molecules on surface compared to those inside the liquid. This means that liquid molecules at the surface have greater energy as compared to molecules inside it. Suppose there is a tumbler. When you pour water in the tumbler, can it get additional energy? Definitely, it will get additional energy due to acquiring free surface. Let us look into two cases when molecules are inside the liquid and when the molecules are at the liquid surface. First case is when molecules are inside the liquid. Suppose there is a molecule inside the water. There will be several other molecules that will attract that molecule in all the directions. As a result, this attraction will bind all molecules together. So, liquid stays together because of this attraction between the molecules. This results in negative potential energy of the molecule as it binds with other all molecules. It depends on the number and distribution of molecules around the considered one. To separate this molecule, huge amount of energy is required to overcome this potential energy. Some external energy is required to move this molecule and it should be greater than the potential energy. So, it is the understandable fact that a large amount of energy is required by the molecules which are inside the liquid for their removal. But the average potential energy of all the molecules is the same. This can justify the fact that to displace a collection of liquid molecules far away from each other, it needs more amount of energy. Actually, this energy is amount of heat energy required by the liquid substance to evaporate or vaporize. It is the amount of energy required by the liquid substance to change its state into gaseous form. This energy is quite large. This is called heat of evaporation. For water, it is of order of 40 kilojoule per mole. It means that for 1 mole of molecules, or 6.023 into 10 the power of 23 number of molecules, it requires 40 kilojoules of heat energy. And second case is when the molecules are at the liquid surface. Let us consider a molecule near the liquid surface. For the molecule which is near the surface, half of it will be inside and half of it is exposed to the atmosphere. For the lower half of the molecule, it will be attracted by other molecules inside the liquid, but the upper half is free. Because of the lower half, the negative potential energy is the half of the previous value. That is, the magnitude is half as compared to the potential energy of the molecule which is fully inside the liquid. It is the reason why molecules on liquid surface have some extra energy as compared to molecules in the interior. Then, what should be the energy required for having a molecule at the liquid surface? You can say that it would be the half value of heat of evaporation of the liquid. That is why a liquid tends to have the least surface area other than no any external force act on it. Increasing surface area requires energy, or to increase more surface area, it gets extra energy. It is the key to understand most surface phenomenon taking place in liquid. Next one is surface tension. It is one of most important topics from this chapter. What is surface tension? It is the property of the liquid which arises due to the fact that the surface molecules have additional energy. That is, it is the extra energy which the molecules at the surface have. So, surface tension is the property of liquid surface because the molecules have extra energy. It is also defined as surface energy per unit area of the liquid surface. It is denoted by S. How is it expressed mathematically? Consider a case in which liquid is enclosed in a movable bar. Slide the bar slightly by the application of the force F as shown in given figure. It moves some distance, let it be d. Then there will be increase in the area which is dl, where L be the length of the bar. Liquids have two surfaces, one on the bar and other above the bar. Therefore, total area increased will be equal to 2 into dl. Then, what is the work done for this change? It will be equal to force into displacement. Since surface tension is the surface energy per unit area, or surface energy is divided by the area, then surface energy is equal to surface tension into area. It is equal to S into 2dl. So, S into 2dl is equal to F into d. Therefore, S is equal to F by 2d. It can be also defined as force per unit length on the liquid surface. What is its unit and dimensional formula? Its SI unit is Newton per meter and CGS unit is Dyne per centimeter. Its dimensional formula is dimension of m t raised to minus 2. The given figure shows schematic picture of molecules in a liquid at the surface and balance of two forces, attractive and repulsive forces in them. You have to bear one important point in your mind. At any interface, the surface tension always acts in equal and opposite direction and it is always perpendicular to the line at the interface. This is the line which separates two different media. They are the air medium and the liquid medium. First figure shows molecule inside a liquid. Forces acted on a molecule due to others are shown. Second figure shows the same thing happened for a molecule at a surface. And third figure shows there is a balance of attractive and repulsive forces. What are practical applications of surface tension and surface energy? You have to see the three different cases and to know about the surface energy in each case. First case is consider a molecule which is present completely inside a liquid and if it is strongly attracted by the neighboring molecules then the surface energy will be less. Second case is consider a molecule which is present partially inside the liquid. The force of attraction by the neighboring molecules is lesser. As a result, the surface energy is more. And third case is consider a molecule whose very little part is inside the liquid. So, very small force of attraction by the neighboring molecules is there. As a result, there is much surface energy. This practical knowledge will be helpful for you to answer the question, what should be the condition for which a fluid stick to a solid surface? A fluid will stick to a solid surface if the surface energy between fluid and solid is smaller than the sum of surface energies between solid air interface and fluid air interface. This means that surface energy of solid-fluid interface is lesser than surface energy of fluid-air interface plus surface energy of solid-air interface. When a fluid sticks to a solid surface, there is intermolecular force of attraction of two different substances. They are fluid and solid. This type of force of attraction is called adhesion. On other hand, if intermolecular force of attraction is there in same substance, it may be either in solid or in liquid or in gaseous substance. This kind of force of attraction is called cohesion. Can you answer this question? Why does water stick to glass but mercury does not? In case of water and glass, water sticks to glass because the surface energy of water and glass is less than the sum of surface energy between water and air and the surface energy between glass and air. That is, SEWG is lesser than SEWA plus SEGA, where Se be the surface energy, the subscripts Wg, Wa and Ga be the water-glass interface, water-air interface and glass-air interface respectively. In case of mercury and glass, surface energy between mercury and glass is greater than the sum of surface energy between mercury and air and the surface energy between air and glass. That is, SEMG is greater than SEMA plus SEAG, where the subscripts Mg, Ma and Ag be the mercury glass interface, mercury air interface and air glass interface respectively. Due to this, mercury cannot stick to the glass. And next question is, how detergents work? You know that washing alone with the water can remove some of the dirt, but it does not remove the grease or stains. This is because water does not wet greasy dirt. So we need detergent which mixes water with dirt to remove it from the clothes. Detergent molecules look like hairpin shape. When we add the detergents to the water, one end sticks to water and other end sticks to the dirt. As a result, the dirt is getting attracted to the detergent molecules and they get detached from the clothes and they are suspended in the water. Detergent molecules get attracted to the water and when water is removed, the dirty particles also get removed from the clothes. As molecules of detergents are hairpin shaped, they use one end to attract to water and the other end to molecules of grease, oil or wax so that they can form water-oil interfaces. You can conclude that the detergent can take the advantage of surface tension for its action. Surface tension is force of attraction between the molecules. In this case, the force of attraction is adhesion. Detergent action in terms of its molecule do is shown in given slide. First figure shows the head of detergent or soap molecules attracted to water. Second figure shows the greasy dirt. Third figure shows water is added but dirt does not get removed. Fourth figure shows when detergent is added, other end of the molecules get attracted to the boundary when water meets dirt. Fifth figure shows dirt gets surrounded by inert end and dirt from the clothes can be removed by moving water. And sixth figure shows dirt is held suspended surrounded by soap or detergent molecules. Dear students, today's homework questions are given in this slide. Please, you have to work out these question answers by today itself. Okay, thank you. Have a nice day.